This is a 6.6 practice. David's iPod has about 10,000 songs. Maybe your phone, 10,000 songs. The distribution of the play times for these songs is heavily skewed to the right. Okay, so our population, you don't have to have this in your homework, but our population, think about how many minutes the song is heavily skewed to the right. Okay, most of them are an average of this much, but there are some songs that are longer. Okay, and this has a mean of 225 seconds and a standard deviation of 60 seconds. Okay, so that's what the population looks like. So for part A, describe the shape of the sampling distribution of X bars for a size of 5. So if I take samples of size 5 from here, okay, sample of 5, find the mean. Sample of 5, find the mean. Sample of 5, find the mean. Okay, if I find all possible samples of size 5, what's that shape going to look like? Well, since this is skewed right, a sample of size 5 is going to be smaller, right? It's not going to be spread out as much. It has less spread, but still skewed right. Okay, whereas B, if I take 100 from this and find the mean, 100 from this, find the mean, that's going to be, it's once again less spread. Okay, because the more that I have in my sample, the less spread out it is, right? But according to CLT, 100 is greater than or equal to 30, therefore my shape is going to be approximately symmetrical, or normal, which is symmetrical as well, but approximately normal. Okay, so then think about those 100 songs. Probably part C, we know it's approximately normal. We know my mean is 225 seconds. Standard deviation is 60, okay? But my standard deviation of our sampling distribution is going to be 60 divided by the square root of 100, right? Taking a sample of, what does it say here? Sample of 100 songs, so of 100. So square root of 100 is 10, 60 divided by 10 would be 6. So I have a new standard deviation, okay? Much less spread out than my population, right? Okay, I want to know is less than 4 minutes or 240 seconds. So 240, I'd say, is about here. So I want this probability right here. Probability that my X is less than 240 seconds. Okay, we've been doing this. Whoop, can't see that. Here's 240 seconds. Probability is less than that. We've been doing this on Desmos quite a bit. I'm not going to show it to you again, but if you have questions, ask me. But the answer is 0.994. Okay, so this is actually should be way up here. Okay, so 240 seconds or less will happen 99.4% of the time. Okay. Okay, question number 2. Okay, question number 2 looked at how many cars. A study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at a suburban interchange. How many people are in the car? Suppose that the number of people per car in the population of all the cars entering the interchange has a mean of this and a standard deviation of this. Could the distribution of people of cars be normal? Okay, in our population. So in our population, okay, could it be normal as part A? Okay, so if our mean is 1.5, okay, so if I think about this, my mean is at 1.5. Now, if it's within 2 standard deviations, would be 95% of my data, right? But if I go 0.75 below, 0.75 below would be at 0.25. So that'd be 1 standard deviation away. And if I go another one, I'd be at negative. Okay, so I can't have a negative amount of people in a car. So therefore, not normal. It cannot be normal. That one's kind of a trickier problem. Okay, can't have a negative amount of people in a car. Okay, so that's part A. So for part B then, part B says, what if I take a sample of 100? Okay, yes. By CLT, 100 is greater than or equal to 30. Therefore, I know the If I take samples of 100, it's going to be approximately normal. Okay, then part C. What is the probability that the mean number of people in 100 cars that come through will be at least 1.7? Okay, so let's think about, we said if it's 100, we know it's going to be approximately normal. Our mean, it tells us that the mean is 1.5 people in every car. And the standard deviation is 0.75 divided by the square root of 100 people, which is 0.075. Okay, so we want to know the prox of 1.7 people, at least 1.7 people. So 1.7 or more is what we're trying to find. Okay, so use your normal and Desmos and get your answer. It is 0.0038. So it is very, very unlikely if I get 100 people coming through and I take the average of those 100 people, that there would be an average of 1.7 people per car. Okay. Question number 3. Okay, that was, let's see here, this problem. Customer service care managers at a cell phone company keeps track of how long each helpline caller spends on hold before speaking to a customer service representative. He finds that the distribution of wait times for all callers has a mean of 12.8 minutes. So we know our population has a mean of 12.8 and a standard deviation of 7.2 minutes. And it is skewed right. Okay, so I know that my population has a skewed right. So if I think about this is my population, skewed right, mean, and standard deviation. Okay. Suppose a manager takes a sample of 45 callers, calculate their mean, and calculates their mean wait time. Okay, so we know that for 45 callers, okay, here's my sampling distribution. We know 45 callers, 45 is greater than 30, therefore with CLT we know it's approximately normal. So I know approximately normal has a mean of 12.8, the same as my population, and my standard deviation is going to be 7.2 divided by the square root of 45. And I'll get my handy dandy calculator here. 7.2 divided by the square root of 45 gives me a standard deviation of 1.07. Okay, now so that's our shape. It's approximately normal. Okay, so if we think about this, part A, what is the shape? We know it's approximately normal. Part B, probability the wait time is more than 15 minutes. So we want 15 minutes or more. Okay, so go to Desmos. Probability the wait time is more than 15 minutes. Go to Desmos and find it. Answer comes up to be 2% of the time. Okay, so if I collect 45 people, find their average, only 2% of the time would it be more than 15-minute wait time. Okay, then the very last one had to do with the same problem. This one here. Explain why you cannot calculate the probability that the average wait time for customer service is more than 15 minutes for a sample of size 5. Okay, I can't do that because I know it's not normal, right? If my population is skewed, I need at least 30. So since n equals 5, CLT does not work to say it's normal, or approximately normal. We need at least 30. Okay. Part B, will the probability referred in part 1 be less than, greater than, or about the same as the probability in 10B? Okay, so let's think about this here. A sample of 5 versus a sample of 45. Okay, we had said, I'm going to do these in 2 different colors. The average wait time was 12.8 minutes, right? So I know here's 12.8. There's my center of both graphs, okay? One of them is going to be skinnier and approximately normal, and the other one is going to be wider and skewed to the right, just like the population ones. Okay, which one's which? Which one of these has a sample of 5 and which is a sample of 45? Okay, so this one here would be the sample of 5. It's still skewed. It's still has a wider distribution, right? This one here is the n equals 45. Okay, it's going to be approximately normal because of CLT, and we know it's going to be less varied because we have more in our sample. Okay, so if I think about a line here at let's say this here is at 15 minutes. So the probability here is much less than this probability right here. So probability when n equals 45 is less than when n equals 5. Okay, with smaller distribution at 15, this area here is very small, whereas if you look at the red, that area right there is very large. So 5 would have a bigger probability.